Hi to everyone. Welcome to Unit 1, Unit 3, Chapter number 1, Special Diodes. Okay, the first concept here, Jenner diode. So everyone carefully listen. Definitely without having the one question related to the Jenner diode, there is no paper at all. That means that is a important concept in this particular Unit 3. So Jenner diode. So in the case of Jenner diode, first we'll see the symbols first. The Jenner diode symbol representation. This is a symbol representation for Jenner diode. Okay, this is a symbol Z symbol, like a Z symbol, Jenner diode. Clear? This is a anode and this is a cathode. It is represented by Jenner diode Z or D. No issue. Okay, practically how to represent the Jenner diode? The resistance of internal resistance of diode in series with the voltage source. Okay, the voltage source here connected. This in the examination they might be asked the question, what is a practical representation for Jenner diode symbol? This is a practical representation of Jenner diode. Okay, in case of ideal case, there is no internal resistance. This is the representation. Okay, these are the three symbols for practical as well as ideal conditions for Jenner diode. So you got some idea about Jenner diode. The Jenner diode itself act as a voltage regulator, because voltage symbol is there, but this voltage symbol like a plus and minus sign, not minus and plus sign, the polarity also somewhat different from the actual diode. We will see everything. So first you need to understand the characteristics of Jenner diode. So VI characteristics of Jenner diode. So Jenner diode having you need to understand two breakdown. Jenner breakdown first you need to understand. Jenner breakdown. Okay. So I will explain what is a Jenner breakdown. In case particular Jenner diode, this particular Jenner diode connected to the circuit with reverse bias. That means negative terminal is connected to anode and positive terminal is connected to cathode. So in that particular case, the value, for example, the Jenner voltage value is a 6 volt. Let me take example. Okay, let me take this is a 6 volt as a Jenner voltage VZ. So for example, you are applying 12 volt. So once you are applying the 12 volt, it means that the Jenner diode, we are applying the reverse direction. That means anode is connected negative, cathode is connected to positive. Jenner diode act as a reverse bias initially. For example, we are applying this particular voltage is a variable. We are applying 1 volt initially. The Jenner diode is a reverse bias. So Jenner diode is not conducting, it acts as an open circuit. Up to we are applying the 6 volt, it is equivalent to 6 volt, then Jenner diode is going to be conducted. So that means that what will happen at the 6 volt? Jenner breakdown occurs. Jenner breakdown means the covalent bonds. Jenner breakdown means covalent bonds by breakdown the covalence bond by breaking. So breaking of covalent. So breaking of covalent bonds by the strong external field, strong electrical field. Got my point? Not a avalanche breakdown. It is a Jenner breakdown. So there is no damage of particular diode. It is a design like that, heavily doped. In the case of P and N junction is there, na? It is heavily doped. So that means whenever you are applying the voltage more than the Jenner voltage, the Jenner breakdown occurs. Jenner breakdown means covalent bonds breaking by the strong electric field you are applied. So whenever you strong electric field applied, Jenner diode is conducting. So it VZ, actual value of VZ is a maintain constant value. If you are more than 6 volt, you are keep on increasing, even though the Jenner voltage is a 6 volt. See here. So in the negative direction we are going to discuss. In the initially the voltage here, this particular voltage is 0. What about the current flowing through the GNR diode is 0. Whenever you are gradually increasing the voltage, so some leakage current will be flowing, up to the GNR breakdown voltage, that is the V6 volt I mentioned here. Whenever it reaches to the GNR breakdown voltage, it breakdown occurs, and then it is current will be increases means that the diode is conducting like as a short circuit. So still we have two current limits. One is a IZ, that is a GNR minimum voltage. That means that after IZ minimum, the GNR diode going to be conducted. After that IZ maximum, this is a safe value of current flowing through the GNR diode. More than that we are applying, GNR diode going to be damaged. So this is about the reverse characteristics. This is about the reverse bias characteristics. Second case we are going to discuss about the GNR diode in the forward bias condition. So what happened in case of GNR diode connected in the forward bias condition. So whenever you connected the forward bias condition, you know this particular voltage, for example you are applying the 12 volt in the previous case. So whenever you are applying the forward bias condition, the current will be trying to flow through the diode act as a actual normal diode condition. The normal diode condition, what will happen whenever diode is forward bias, whenever it reaches to the some minimum voltage, for example it is a silicon 0.7, in case of germanium 0.3 volt, then diode will be conducting. So in the same case here also, whenever you are applying the 12 volts in the forward direction, somewhat up to some voltage, up to, for example it is germanium, will take 0.7 volt, it acts as an open circuit. So after 0.7 volt, diode going to be short circuited, like diode going to be conducted as a normal characteristics. So this is the same as normal characteristics of diode. It is act as a diode is a normal diode whenever it is connected in forward bias. So whenever it is connected in reverse bias, it acts as a GNR diode. Okay, so this is the normal condition, this is the GNR breakdown condition. Okay, all of you clear about? If your GNR diode operated in the forward bias condition, what will happen? It acts as a normal diode. Whenever GNR diode connected in the reverse bias, it acts as a voltage regulator. GNR breakdown occurs. So let us discuss. All of you clear about the characteristics? Yes. Then we are moving to the GNR voltage. The first terminology, the GNR voltage. So GNR voltage. So we'll see what is the GNR voltage already. The voltage, the minimum voltage of the minimum voltage of the diode, GNR diode. After that, the voltage being constant, the GNR diode going to be conducted. The available GNR diode voltage is up to 2.4 volt to 200 volt. That is a voltage available for the GNR voltage. You are going to design practically. This voltage is depending upon the temperature. Very, very important. GNR voltage is depending upon the temperature. So it is a temperature dependent. It is a temperature dependent. Okay. Next one, GNR biasing. So in case of GNR biasing, we'll see to properly bias the GNR diode, the following conditions going to be required. The first one, the diode should be reverse bias. That is the first condition. So if you want to utilize the GNR diode complete applications, the GNR diode should be connected reverse bias. The second case will be the voltage across the GNR diode is greater than VZ. So voltage across GNR diode is greater than VZ. Okay, that is the second case to properly bias the circuit. Third condition, circuit where current is less than, always current will be less than, current is less than IZ maximum. This is about the GNR diode biasing conditions. So everyone is clear about up to till voltage of Zener diode and Zener diode biasing. Then we are moving to the how to identify the Zener diode. How to identify the Zener diode. All the diodes are look like same based on the numbers you are going to identify. So how to identify here? In this is a Zener diode identification in the symbol, but in the practically every diode they mention the IN. For example, IN750, that is a Zener diode with the wattage of 10 watt power. That is the first Zener diode. Second type you can also represented IN is a 4000, that is a high power Zener diode. High power Zener diode. That way, based on the numbers, you can number present in the diode body, we can identify that is a Zener diode. Clear? Next, we'll see uses. So uses of Zener diode. Already I mentioned that Zener diode act as a voltage regulator. So it does also act as a common reference point. Zener diode as well as fixed reference point. It is a peak clippers. So meter protection for the to protect the meter from the unwanted signals, like accidental applying more voltages. So all these applications we will see one by one. Okay, the first case, Zener diode act as a voltage regulator. Then we are moving to the remaining two applications are meter protection, Zener diode as a peak clipper. Then we will complete the Zener diode concept. So we'll see first of all problems related to the Zener diode. Okay, first we'll see the first problem. Determine the whether ideal Zener diode, very important, ideal Zener diode in the figure, it is properly biased or not. Explain why. But we are not writing a theory examination, we are writing the objective examination. That's why in the examination point of view, they will provide this circuit. They will ask the question like that, whether Zener diode is properly biased properly biased or not. They will give the some options like that. You can, otherwise numerical problem they will provide. See, in this particular case 6 volt is the input. You should understand 6 volt as an input. What about the Zener voltage is a 10 volt. To properly bias, I gave the three conditions here. The voltage across the Zener diode should be greater than Vz. So here the voltage across the Zener diode is 10 volt, but you are applying the voltage across this particular Zener diode is less than the 10 volt. That means Vz value is less than the V input. That means less than. So that means Vz is greater than input voltage. That input voltage is less, then Zener diode is not properly biased. Zener diode is not properly biased. That means what happened? Zener diode act as a open circuit. Clear about the first problem? Next, second problem we are going to see. Find out Zener diode shown in the figure properly biased. So find the diode current assuming when it is ideal. Ideal means that there is no internal resistance. So this type of questions they may be asked in the examination. First of all, see 12 volt and then 10 volt. Which one is a greater? Input voltage is a greater. That is the condition is satisfied. Whenever input voltage is greater than the Zener voltage, so diode is properly biased. So another important point, positive and negative. Positive terminal connected to anode and the negative terminal is connected to cathode. That is the first condition I forgot to explain. So it is a reverse bias. The input voltage is greater than the Zener voltage, then it is a properly biased. Polarity wise is properly biased, voltage wise also properly biased. Whenever it is a properly biased, Zener diode is a conducted state, that means on state. It acts as a short circuit, right? That means on state, conducting state. Whenever it is a conducting state, what will happen? The voltage across here 10 volt. It acts as a voltage source, 10 volt. The 10 volt polarity should be already given in the previous case. That this is a representation for ideal case. So this is a 10 volt. Then we will going to draw the circuit here. It is a 12 volt and then it is a 500 ohms. After that, this is the voltage is 10 volt. Clear? Now the current will be current I. Current will be, they are asking I is equal to 12 minus 10 divided by 500. So that means that it is a 2 by 500. So 2 by 500, it is approximately 4 milliampere. That is a voltage in the circuit. That is a voltage in the circuit once it is Zener diode is properly biased. Clear? Then we are moving to the another example. Maximum 2018 question paper and 2017 question paper and 2014 question paper and 2016 question papers, Zener diode two question papers having a problems, numerical problems they provided. So you need to focus on numerical as well as some important theoretical bits also in this particular case. Definitely one bit will be there in the examination. So Zener diode, determine if the Zener diode shown in the figure is biased properly or not. So if biased properly, find IZ and the power dissipated by the diode. That is a question here. So in that question, the first thing you need to identify that whether it is a properly biased or not. First, polarity wise we'll see. It is a positive, it is a negative, right? Whenever it is a positive, it is a negative. So the Zener, it is a positive, it is negative, it is a reverse bias. Okay, first condition is satisfied. Zener diode is connected in the reverse bias condition. After that, whenever it is reverse bias condition, what about the input voltage 18 volt? What about the voltage here 12 volt? Definitely, this is a 12 volt, this is 18 volt, it is conducting. What is the voltage drop here? 6 volt. That means that this Zener diode is conducting. Once this particular Zener diode is conducting, we can find out the Zener voltage is a 12 volt, right? Hence R1, the voltage drop across R1, that is a voltage drop across R1, we can call it as a V1. 18 minus 12, that is a 6 volt you got. From that you can calculate the current flowing through this particular resistor, that is a current I is equal to V by R. V is a 6, R is a 600, R1 is a 600. So that will be equivalent to 10 milliamperes. Got my point? You got 10 milliamperes is a total current. Now, what is the current I1? The current will be divided into two cases. The first case, here voltage is a 12 volt. This is a parallel. The first case, I1 is equal to V, that is a VZ, because parallelly connected 12 divided by 1800. Why it is why you are taking 12 volt? Because Zener diode, once the Zener diode is conducting, the 12 voltage is a constant. Without we are increase the voltage further also no issue. The voltage across the 1800 ohms is a 12 volt only. Remaining all the voltage drop across the 600 only, it will be appears. Okay. So Zener diode always it act as a constant voltage regulator. 12 volt is always present. So then you will get the 6.7 milliamperes. So finally the Zener voltage, you want Zener voltage, Zener current, that will be equivalent to total current, that is a 10 amperes minus the current flowing through the I1, that will be equivalent to 2.3 milliamperes. What is the maximum voltage? It is mentioned 6 milliamperes. You got the Zener voltage is a 2.3 milliampere. That means that the Zener is working in the properly. Okay, there is no problem at the Zener diode working condition in this particular specifications. Clear? Then we are moving to the next example. In the next example, calculate the E0. Calculate the E0 in the given circuit. Vn is equal to 6 volt. Vn is equal to 6 volt. Whenever it is a 6 volt, it is a negative, it is a positive. Whenever it is a negative, it is a positive, it is a negative. That means Zener diode is reverse bias. But Zener voltage is a 10 volt. But you are applying the input voltage is 6 volt. That means that the input voltage is less than the Zener voltage. Diode act as a off state, open circuited. This particular diode act as a open circuited. Okay, this diode act as a open circuited. What about the E0 value? E0 value is equal to 0. This particular diode is seriously connected. So whenever it is act as open circuited, so our circuit will be like that. So everyone listen carefully. It is a series connection, right? Series connected diode. Even though here 6 volt, it is open circuited. There is, so here open circuited. Okay, here E0 will be 0. Here 6 volt total ante 6 volt present here, open circuited. There is no connection between the input and then output, so E0 is equal to 0. This is the first case whenever V is equal to 6 volt. Second case we are going to discuss. In the second case, V is equal to 12 volt is given. See here, GNR voltage is 12 volt. Input voltage is 12 volt. So whenever input voltage is a 12 volt, so what will happen? It is a 12 volt more than the 10 volt. That means GNR diode is conducting after input voltage reached to the 10 volt. Whenever input voltage reached to the 10 volt, so it is act as a what we call it as act as a GNR diode, conducting on state, act as a battery of 10 volt. This is the polarity of the source, GNR diode. So whenever this is the polarity of a source, so it is connected some resistor, it is 100 ohms. Now you want V0, right? So Vin is equal to 12 volt. You want E0 value. Now this is the polarity plus and minus. What is the polarity now? Voltage appears here, V is equal to, so otherwise E0 is equal to, this is the polarity 12, it is opposite polarity 10, then you will get the 2 volt. What is the output voltage now? Okay, but here not 12 volt is given, it is a 20 volt is given. Just see, I am sorry. So what is the voltage is given? 20. Okay, that means that 20 minus 10. What is the 20 minus 10? 10 volt is the answer. So clear everyone? Then we are moving to the further problem. First we are going to discuss about the first application, voltage regulation. After that we will discuss few more problems. So voltage regulation, GNR diode act as a voltage regulator. So we'll see how GNR diode is act as a voltage regulator in this particular case. So first of all, we'll take up the two cases. The first case, the condition here, the plus sign and then minus sign connected to the GNR diode in the reverse bias condition, right? Whenever it is connected reverse bias condition, covalent bonds going to be breakdown. So whenever it is reached to the input voltage, reached to the more than GNR voltage, GNR breakdown occurs. GNR breakdown occurs. Whenever GNR breakdown occurs, GNR diode going to be conducted. So in that particular case, the current I, this current IZ, so I is equal to, the current will be I is equal to IL plus IZ. The total current will be equivalent to IL plus IZ. So what is the voltage drop across the output? The voltage drop across the output is equal to I into IL into RL. What about the voltage drop at the input? Voltage drop at the input, it is a, for example, it is a VZ, the voltage drop here VL. What is the voltage drop in between these two resistors? Will be, the voltage drop will be V input. The voltage drop here IR, current into resistance, that will be I into R plus VZ. That is a total voltage. So we are considered two cases. So this is about this particular voltage regulator circuit, how it will be hacked, and then which quantity parameter going to be changed, even though the voltage will be constant. We'll explain now the case 1. The first one is a case 1. In the case 1, what will change? Here R is kept constant. So that means that load resistance should be constant. What we have to change? We have to change increasing or decreasing the input voltage. So in that particular case, we are going to analyze the circuit parameters. So in that particular case, what will happen? See here, whenever suppose R is kept constant, fixed supply, the input voltage is increasing slightly. Whenever input voltage increasing slightly, it will increases the current. Whenever the input voltage increases, what will happen? The current going to be increases. Whenever current increases, this increasing current absorbed by this particular increasing current absorbed by the GNR voltage, GNR diode, without affecting the IL. That means that this IL will be constant. The current taken by the GNR diode increases. the increasing will be dropped, the increasing voltage will be dropped across this particular resistor. Okay, so across this particular resistor, then V output is kept constant. What is how to V output? V output is same as Vz. So even though the drop appears across this particular one, the voltage drop across the G0 diode is Vz. Always it is a make a constant. So whenever V falls, for example, V decreases. So whenever V decreases, in that particular case also, the drop across resistance is decreases, the Vz remains constant. Likewise, whenever we are increasing the input voltage or output voltage, voltage is constant. That's why it is called as a voltage regulator. So all of you got an idea how to constant voltage, whether we are increasing or decreasing the input voltage, the keeping the load resistance kept constant. Case 2. In the case 2, you know, V in is fixed, that is the input voltage is a fixed one, so constant. Then but IL is changed, load current will be changed. How to change the load current? To change the load resistance. So see here, how to whenever you change the load current, what will happen, we will discuss now. So I need to erase this particular things. So just focus here, otherwise I will copy this particular circuit. Right. See in the second case, IL should be vary, input voltage is a constant. How if you change the IL? So whenever the input voltage is a constant, the drop across the R is constant. So whenever the current will be increases IL, so what will happen? We'll see with the help of the formulas. So in the case of V is a fixed, IL is changed, IL increases. Whenever IL increases, so the diode current IZ decreases. Whenever IL increases, because you are applying the constant input voltage, that means the constant current will be flowing. Whenever this IL increases, what about the IZ decreases? So whenever IL increases, so keeping I is a constant, so kept I is a constant, that means that this I is a constant, so hence IR top is also constant. This is the way V output is unaffected. The output voltage across this particular load is not changed. That is the first one. Now we are decreasing the IL going to be decreases. What will happen? IL decreases, I should become increases, IZ became increases. What will happen? IZ increases. So in order to keeping which one is a constant? I is constant. Okay, current will be constant, that is IR drop is a constant. Again this particular output, what about you are supplying this particular output is same as GNR voltage. So you can also maintain the output voltage always constant irrespective of your input is increases or decreases. So now the output is equal to V in minus IR. The output, this particular output is equal to V in minus IR, that is the output voltage across here. You know, V in, what is the current? I is nothing but a IZ plus IL. You know that. Apply KCL here. I is equal to IL plus IZ. Into resistance is there, resistance R. So from that, resistance R is equal to V in divided by IZ plus IL. In that particular case, I make it this load resistance is 0. Load current will be 0. What will happen? IL will be 0. So finally, here there is no more. Finally, we are V in divided by IZ. Maximum. This is about the formula. Whenever the resistance you need to calculate whenever IL became 0. These two formulas you need to remember to find out this particular condition. Okay, so this is about the GNR diode case. Then we are moving to the next problem. The problem number 5. Calculate the battery current I. You need to calculate this current IZ, yes, and IL for the circuit. How will be values be affected to source voltage increases to 70 volt. Just we discussed the input voltage increases to 70 volt. Neglect the GNR resistance. Neglect the GNR resistance. We'll see the first case. Case 1, Vin is equal to 40 volt. Here given Vn is equal to 40 volt. What about the VAB? VAB is given, that is a GNR voltage is given. VAB is equal to 10 volt. Okay, so whenever VAB is equal to 10 volt, okay, VAB is equal to 10 volt. What is the resistance? Series resistance is given. Series resistance is given 3K. So whenever it is a 3K, the voltage across series resistance, we can take it as a Vs, for example, V series resistance, voltage drop is equal to 40 minus this particular 10. So what is the voltage drop here? 30 volt. Clear? So I got the voltage drop is 30, then total current will be 30 divided by 3K, it will be 10 milliamperes. What is the total current here now? 10 milliamperes. Once you got the total current, load current IL is equal to VZ. Load current IL is equal to VZ divided by, VZ is nothing but the voltage across GNR diode is same as load voltage here. Okay, IL. So VZ by RL. So what is the VZ? 10. What is the RL? 2K. That will be equivalent to 5 milliamperes. So IL is a 5 milliamperes. Finally, IZ is equal to 10 milliamperes minus 5 milliamperes. It will be equivalent to 5 milliamperes. What is the maximum? They provided the power here, 0.5 watt. Okay. So IZ is got 5 volt. So P maximum is equal to IZ into VZ. What is the IZ? 5 milliamperes. VZ is equal to 10. So the power will be, you need to calculate the IZ maximum, right? V maximum is equal to VZ maximum, IZ maximum into VZ. So here P maximum. What is the P maximum is given? 0.5. IZ maximum you need to find out. So VZ is given 10 volt. So from that IZ maximum is equal to 0.5 divided by 10, that will be equivalent to 0.05 amperes. It will be equivalent to 50 milliamperes. What is the IZ maximum? 50 milliamperes. This is about whenever the voltage will be 40 volt. After that, we are going to increase the voltage to 70 volt. So whenever increase the voltage to 70 volt, the voltage across the resistor is equal to 70 minus 10. That will be equivalent to 60 volt. Again, we are going to calculate the total current I is equal to this particular V divided by resistance in the circuit. What is the resistance in the circuit? 3 kilo ohm, right? This is a 3 kilo ohm. So the resistance in the circuit is a 3K. So that will be equivalent to 20 milliamperes. Okay. So finally, IL is equal to V. So you got I current. IL is equal to, you got in the previously 5 milliamperes. The current will be at the load. So finally IZ is equal to I minus IL. What is the I? 20 milliamperes minus what is the IL? 5 milliamperes. That means it is a 15 milliamperes. So it is keeping that the voltage at the whenever your input voltage increases, the keeping that VZ is a constant across the load, it takes more current. Whenever increase input voltage is more, just now we discussed in the theory, it is the current value of the GNR diode increases, okay, up to 15 milliamperes. So but GNR voltage is a constant. This is about the example problem about the theory explanation. Then we are moving to the example 6. Next problem 6. So in that particular case, we are going to discuss about using ideal GNR diode approximations, find the current through the diode. So in the figure, so we have a 3 resistor concepts, that is a 30 kilo ohm, 5 kilo ohm and 3 kilo ohm. That means that previous example we discussed about the input voltage change. If you change the resistance about the output, what will happen in the circuit parameters we are going to discuss. So first case, I am taking about 30k, right? 30 kilo ohm. When I am taking about the 30 kilo ohm, this is 30 kilo ohm in the first case. So VAB, the voltage across the J0 diode will be, VAB will be 30 volt. That is a constant. So after that, VAB is a 30 volt, that is irrespective of the load you are connected, irrespective of the input you are connected, that is a 30 volt. So after that, it is connected forward bias or not, that is a reverse bias or not, plus and minus, it is reverse bias, okay, satisfied. Then only can choose for further calculations. Without checking this polarity, if you are going to do the calculations in the examination, so everything is wrong. So first condition, you should be reverse bias, then only can go forward about the calculations. So Vz is equal to 30. Voltage drop across the resistor is equal to 60 minus 30, that will be equivalent to 30 volt. That means what is the current? I is equal to V by R. 30 divided by 3, that will be equivalent 3K, that will be equivalent to 10 milliamperes, that is a total current supplied by R. So once you got 10 milliamperes, IL will be, that is the voltage across the current flowing through the load resistance will be 30 divided by 30K, that will be equivalent to 1 milliamperes. So IZ is equal to GNR current will be equivalent to I minus IL, you know the formula, I minus IL according to KCL. Total current is equal to, you want the current value IZ, GNR current. IZ is equal to I minus IL. So what is the I10 minus 1, that is a 9 milliamperes. Just keep it in mind. What is the current you got? GNR current 9 milliamperes. We'll see what will happen if resistance is decreases to 5 kilo ohm. The second case, resistance is decreases to 5 kilo ohm. We are going to discuss about that. So see here, whenever it is a 5 kilo ohm, the load resistance is 5 kilo ohm. Now we are going to calculate the voltage, the current will be same, that is a 10 milliamperes. It is not changed because the input voltage is a constant. So what about IL? IL is equal to 30 divided by 5K, that will be equivalent to 6 milliamperes. The load current will be changed because you are changing the resistance, but keep it in mind, Vz is always constant, that is a 30 volt. Now Iz will be equivalent to I minus total current minus 6 amperes, 10 milliamperes minus 6 milliamperes, that will be equivalent to 4 milliamperes, that is a GNR current 4 milliamperes. Okay, it is GNR current. What will happen? GNR current here 9 milliamperes is here 4 milliamperes. GNR current decreases. Okay, after that we are going to take 3 RL is equal to 3 kilo ohm. That means that we are further decreasing the resistance. Indirectly means that whenever you are decreasing the resistance, IL going to be increases. What about GNR voltage going to be decreases, because you are keeping current I is a constant. Just now in the theory class, what I explained in the previous, this particular video, at the 10 to 15 minutes after explanation, I mentioned this particular relation. IL increases, load resistance increases in the case 2, GNR diode decreases, the keeping current I is a constant. Again we are going to take up the third case, 3 kilo ohm. Again here current is a constant because the input voltage here maintain constant. What about load current will be changes because 30 divided by V is a 30 divided by voltage is a constant by what is a 3K, that will be equivalent to 10 milliamperes. For that GNR current will be 10 minus 10, it is what, 0 amperes. So got my point. Whenever it reaches to this particular resistance is equivalent to the load resistance, then GNR diode voltage will be 0. In the examination, don't do all the calculations, maybe some logic will be there. Whenever your input voltage is a constant, some fixed voltage, load resistance, the load resistance is same as the connected resistance in series with the source, then GNR current will be 0. The current flowing through the GNR diode going to be 0. That is the condition you need to identify. Remember that. Okay, then we are moving to the one more problem. Then we are going to the next topic, GNR diode as a peak clipper. So in that particular case, 24 volt 60 milliwatt GNR diode is used to provide in the 24 volt stabilizer, right? So variable load, stabilizer variable load. The input voltage is 32 volt. Calculate the series resistance required and diode RL is, in the second case diode RL is 1200 volt. This type of problems may be in the examination. You will see in the first case. What is the first case? It is provided the maximum power P maximum is equal to 600. That is a VZ into IZ maximum is equal to 6.6 means 0.6 watt. That is a 600 milliwatt. So from that IZ maximum is equal to, what is the voltage here? 24, right? That is a 600 divided by 24. It is a milli, right? So 25 milliamperes. So I got Z maximum is equal to 25 milliamperes. From that, you know, R is equal to, I gave the one formula, V in minus V out divided by IZ maximum. IZ maximum. This is the formula I provided in the theory. So what about R, this particular resistance? Otherwise you can, you know, this is a 24 VZ. V in minus V output. For example, this is a parallelly connected, here V output. V in minus V out by V out by current will get the resistance. So that is 32 minus, what is the voltage? 24. This is the voltage 24 divided by IZ maximum is 25 into 10 power minus 3. Then you will get 320 ohms. This is the way you need to calculate the resistance required to connect it there. In the second case, if load resistance is equal to 1200 ohms, what about the parameters they are asking? GNR current. So load current will be IL is equal to VZ by RL. What is the VZ? 24. RL is equal to 1200. So from that, IL is equal to 20 milliamperes. Once IL is equal to 20 milliampere, IZ is equal to, already Z maximum is a 20 minus 20, that will be equivalent to 5 milliamperes is a current. So you got two cases, R resistance as well as current. Okay. Then we are moving to the next important topic, GNR diode as a peak clipper. GNR diode act as a peak clipper we are going to discuss. In this particular diagram, input here connected sine wave. So everyone listen carefully. I will explain some suitable examples. Whenever you are connected positive half cycle, now this diode positive you are connected, negative you are connected. That particular diode act as a normal diode, forward bias condition. Next coming to here, this particular voltage source you are connected negative, you are connected positive. Diode D1 is a forward bias. Diode D2 act as a reverse bias. Okay, it act as a normal diode. It is act as a GNR diode. Once you are applying the voltage more than VZ, GNR voltage. So initially what is the voltage present here? VZ is equal to 620 volt. Once the input is before 20 volt, what about the diode D2? D2 is a open circuited. Diode D2 is a off reverse bias before 20 volt. So after 20 volt, this particular diode already it is a forward bias, is conducting. Diode D2 also act as a conducting, and that means that it acts as an on switch. Whenever it is act as on switch, both the diodes are conducting after 20 volt. What about the voltage drop across here? Total entire 25, above 25 volt drop here. What about the output voltage is present? The output voltage present is same as 20 volt, constant. We are increasing the voltage more than the 20 also, the 5 voltage drop across this particular diode D1 and D2. So the clipping above 5 volt is clipping to the waveform. So similarly, in the second case, negative half cycle is given. This is the negative, this is the positive. This particular D1 act as a forward reverse bias, and D2 act as a normal diode. In that particular case, once you reach the negative 20 volt, the total entire voltage drop is maintained minus 20. After 5, that remaining 5 volt dropped here, dropped in the resistor. So that means that total entire thing is clipped. This is the waveform for this input. So this is about the GNR diode clipping some part of the input signal. Next, coming to here, this particular GNR diode is connected to GNR diodes, here 50 volt, here 10 volt. In that case, whenever it is reached to the 10 volt, in the first case 10 volt, this up to that GNR diode is open circuited. What about the voltage 10 volt present here? Once you reach the 10 volt, normal working condition diode is conducting, GNR diode is also conducting, it maintains 10 volt. So 10 volt constant. In the negative half cycle, up to minus 10 volt, it is act as a open switch. After 10 volt, whenever it is a closed switch, total entire voltage drop here, it is a clipping. This is a circuit waveform for output. So all of you clear about the GNR diode act as a clipper? Right. Then we are moving to the next topic, meter protection. Okay, this is the last topic. So how to protect this particular meter with the help of the GNR diode? In this particular case, this particular GNR diode is conducting anti-parallel to the meter. Whenever it is connecting anti-parallel to the meter, what is a plus here minus? This is the GNR diode act as a reverse bias. This particular GNR diode act as a reverse bias condition. So initially, for example, this particular meter able to measure 2.5 volt. So this 2.5 volt, this particular GNR diode can design some value. Instantly, whenever you are by mistake you are connected, instead of 2.5 volt, I connected 25 volt. I connected 25 volt. In that particular case, the GNR diode is designed for some precaution value, it is 2.5. For example, I can design this particular GNR voltage will be 2.5 volt, 2.6 volt otherwise. Whenever you design for 2.6 volt, we are connected more than 2.5 volt here, otherwise 25 volt. Whenever it is more than the 2.6 volt, GNR diode going to be conducted. Whenever it is conducted, what will happen? Total entire is diverted, the current from here, the meter going to be safe. Okay, that is a protection for the meter in case of GNR diode. Whenever you are connected to GNR diode anti-parallel, we can also overcome the overload condition also. You can protect from the overload. So this is about the meter protection. So in the examination, they will provide this particular circuit. This particular circuit is related to the meter protection, otherwise meter. So it protect the overload condition. This particular circuit is related to. Okay, this is about the GNR diode complete explanation. Next class in the lecture number 2, we are going to discuss about the tunneling effect. Okay, thank you.